Welcome to our lecture on defining the derivative. So first, let's talk about some things that we already know. So here's this curve f of x, the blue curve here. And let's say we're interested in finding out what the slope of the tangent line to that curve is at the point a f of a, where the x-coordinate is a and the y-coordinate is f of a. Well, what we did prior to now is that we used the slope of the secant line. The secant line intersects f of x at 2 points, and we moved this point, x f of x, closer and closer and closer to a f of a, and the shorter the secant line segment, the closer we were to approximating the actual slope of the tangent line at x is equal to a. So as we move that point closer and closer and closer to a, we found that we could converge on the slope of the tangent line at the point a f of a. All right, so now we're going to talk about the slope of the tangent line from another perspective. So now let's talk about slope as a difference quotient. So the equation for the slope of a secant line can also be called a difference quotient, which means you have a difference in the numerator and you have a difference in the denominator, and then they're divided with this, which is your division bar. All right, that's what we refer to as a difference quotient. So now, if we let x equal a plus h, where we introduce some new variable, h, then f of x is equal to f of a plus h, where wherever we have an x, we substitute an a plus h in whatever function we're dealing with. Now this h value is a very, very small value. It's very close to 0. So now, if we look at the slope of the secant line through these two new points, a f of a, and then this other point where the x value is now a plus h, that's a little bit past a, and substituting a plus h into the function, we'll get the y value. So our slope of the secant line, this is how we're used to seeing it, can now be written like this. So where we substitute a plus h for x, and then f of a is still the same thing, f of a, x is now a plus h. Right, so the numerator is just going to look like that. Nothing's going to cancel out. But in the denominator, the a's are going to cancel out. So now what happens, and this ends up to be a really useful thing, is that we just have this h in the denominator, and we're able to use this difference quotient here to help us define what we're going to call the derivative. All right, so we call this difference quotient here the difference quotient with the interval h, or over the interval h, which is a very, very small interval. So here's a diagram of what I just was talking about. So we've got the same curve, the blue curve, but now we're calling this point over here an h distance past a. So this is an x value, this is an x value. So we have x, and then we have substituting a plus h into our function, we're able to get the y value. All right, so now we've got this point and we've got this point. All right, and we can write the slope of the secant line in this form here. Okay, so as h approaches 0, that means as this gets closer and closer and closer and closer to a, the 2 points are going to get closer and closer. And the slope of the secant line will approach the slope of the tangent line at a. So we now have the following definitions for the slope of the tangent lines at x is equal to a if the limit exists. So this is the one we're used to. All right, this f of x minus f of a over x minus a. But we can write it as a limit now. We understand limits a lot better than we did before. We can say the slope of the tangent line is the limit as x approaches a of this difference quotient here. All this is saying is that a and x are very, very close to each other. All right, and that means this point right here is moving very, very close to this point, and the closer you get, the better the approximation is for the slope of the tangent line. Okay, we can use it in that form, but we could also use it in this form, where we've only got this one variable in the bottom, h. So as this distance h between here and here closes up, gets closer and closer to 0, right here, this is the slope of the tangent line. And the closer we get, the better the approximation to the slope of the tangent line becomes. So now let's talk about what we mean by a derivative. So the type of limit, and what I mean is this type of limit, are used so frequently in disciplines such as physics, biology, business, math, etc., engineering, that it has a special name, and we call it the derivative. And the process of finding the derivative we call differentiation. It also has a special symbol, the accent mark. We call that a prime. So this symbol right here, we say f prime of a means the derivative of f evaluated at a. Okay, so that is what we call a derivative. All right, so these special limits right here, and you could be in this form or you could be in this form. All right, these are the same thing, just a different form, but you get the same number in the end. You could use this or you could use this, but you would get the same number. And we're going to do some of this. Let's do example 1. It says find the slope of the tangent line to the graph of f of x is equal to x squared at x is equal to 3 using definition 1. So here's definition 1. So slope of the tangent line is equal to the limit as x approaches a of the difference in the y's over the difference in the x's. So let's go ahead and apply this definition to find the actual number for the slope of the tangent line at x is equal to 3. So what we're really saying here is that if we can evaluate this limit, then we will have an exact number for the slope of the tangent line, and we can use this method instead of having to make a table of values. So we're going to say equals the limit as x approaches 3, which is our x value of interest, and we call that a, of f of x, that's x squared, minus f of a, which means I substitute 3 in there where the x is, and then I've got x minus 3. X squared minus 9 over x minus 3. Now it looks like we have a removable discontinuity, because if I factor this difference of perfect squares, I'm going to be able to remove that discontinuity that occurs because of the 0 in the denominator. So I can say the slope of the tangent line, now I can evaluate this limit as x approaches 3 of x plus 3 by just substituting 3 into the polynomial. All right, so we know that we can get an exact value by substitution. So the slope of the tangent line is simply 3 plus 3, which is 6. All right, so that's a lot easier than having to approach from the left and the right like we had been doing with tables. So example 2, we're going to verify that we get the same answer, 6, by using definition 2 instead of definition 1, because we said that, let's go back there, we said that these two definitions are going to give you the same number, the slope of the tangent line. So let's just show that that works. So slope of the tangent line, just doing some substitution here, is equal to the limit as h approaches 0 of f of 3 plus h, right? So this is your a, minus f of 3 divided by h, which is the limit as h approaches 0. So f of 3 plus h means that I substitute 3 plus h wherever I have an x in my function. So I have one place where I need to substitute 3 plus h, and then I square it. Square a binomial. Now here, f of 3 means I find the y value when x is 3, so that would just be 3 squared. Let's just put that here, 3 squared, which we know is 9, over h. All right, so now let's square that binomial. So we have the limit as h approaches 0 of 3 plus h. Of course, you got to remember how squaring binomials is always happening from now on out here. Okay, so I have that. So I've got 9 plus 3h plus 3h plus h squared minus 9 divided by h. All right, so I can cancel the 9's here and here. So I've got 6h plus h squared over h. All right, so we wanted that h to cancel in the denominator, so we're able to evaluate this limit. All right, so if that doesn't happen, then we've got a problem. So now we can evaluate the limit. So this is going to be the slope of the tangent line. The limit as h approaches 0 of 6 plus h. Well, that's just a polynomial, so we know we can just substitute 0 in for h. So we did get the same number, 6. We just did it in a little different fashion. And that's what we expected to happen. Either one of these definitions, 1 or 2, should give you the same slope of the tangent line. So example 3 says, find the slope of the tangent line to the graph of a new function, f of x is 1 over x this time, at x is equal to 2, using definition 1. So I wrote definition 1 down, and we're going to do our substitutions. So the slope of the tangent line is equal to the limit as x approaches 2 this time. This is your a here, of f of x. F of x is 1 over x, minus f of a. A is 2, so that's 1 over 2, divided by x minus 2. So we're going to simplify this to see if this limit can be evaluated. So now I'm going to multiply 1 over x by 2 over 2 to get a common denominator of 2x. And here I'm going to multiply 1/2 by x over x to get a common denominator. So I'll have 2 minus x in the numerator, 2 minus x, and I'll have 2x, my common denominator, and then that'll be divided by x minus 2. Let's just put a 1 under that. All right, and we know we can say this is 2 minus x divided by 2x, flip and multiply. All right, so remember we called these reverse factors. These will cancel, but you're left with a negative here. So we've got negative 1 divided by 2x. All right, so now we want to take the limit as x approaches 2, which we can now do because we won't get a 0 in the denominator, of minus 1 divided by 2x. So that's a rational function which, if it's continuous at the x in question, you can evaluate the limit by just substituting the x value into the function. All right, so it is continuous there. That new function right here is discontinuous at x is equal to 0, but we're here at 2. So we're just going to substitute 2 in there. So that's equal to minus 1 divided by 2 times 2, which is minus 1 over 4. All right, so this is the slope of my tangent line. So example 4 says, find the slope of the tangent line to the graph of f of x is equal to the square root of x at x is equal to 4. So this is your a, this time using definition 2. So I wrote down the definition. So now we're going to do our substitutions. So the slope of the tangent line is going to be this limit. Limit as h approaches 0 of f of, let's just write this out here, 4 plus h minus f of 4 divided by h. So I'm going to substitute 4 plus h wherever I have an x in my function. So that would be the square root. I only have one x in my function, 4 plus h. And then I'm going to evaluate my function at 4, which would be the square root of 4 all over h. So that's the same thing as 4 plus h minus 2 divided by h. All right, so what we learned when we were finding ways to evaluate limits is that if you have a difference involving a square root, we can multiply by the conjugate and see if we can change the form such that we can evaluate this limit. All right, so I'm going to say limit as h approaches 0 of all of that multiplied by the conjugate, which means I change that minus to a plus. All right, so there we go. So now I got to carry out all this algebra and see how this simplifies. So the square root of 4 plus h times the square root of 4 plus h is 4 plus h because the radical comes off. Then I've got 2 times that here. And then I've got minus 2 times this. So those are going to cancel out, which happens when you multiply by the conjugate. And then I've got negative 2 times 2 here, negative 4. And then in the denominator, remember we don't go ahead and multiply this out because usually we can get something to cancel. And we don't want to obliterate it by combining all those terms in the denominator. All right, so let's cancel these out here. And then I've got 4 minus 4. All right, so I'm just left with h in the numerator and h in the denominator. So all of that cancels out, and I'm just left with 1 in the numerator. And then in the denominator, I've got the square root of 4 plus h plus 2. So if I take the limit of that as h approaches 0, I'll be able to evaluate that limit because I won't have that 0 in the denominator anymore. All right, so that's 1 over the square root of 4 plus 0 plus 2, which is equal to 1 over the square root of 4 plus 2, which is equal to 1 over 2 plus 2, which is equal to 1 over 4. Okay, so I was able to evaluate that limit and find an exact number for the slope of the tangent line at x is equal to 2. Actually, x is equal to 4. All right, so this is my slope of the tangent line at x is equal to 4. So in example 5, we're going to talk about definition 3. And we're going to use a table of values, once again, to estimate the derivative f prime of 3, the derivative of the function f, evaluated at 3, where f of x is x squared, and the x value in question is 3. All right, so let's go back to definition 3, and this is when we start to talk about this being a derivative. All right, so we call it, it has its special name, remember, because it's used a lot, f prime of a. So we're going to use this definition here in our example 5. So I wrote down definition 3, so we can see this is just the difference in the y's over the difference in the x's, and we're going to find the limit of that. So we did this quite a bit in chapter 2 when we were working with limits, and we used tables. So let's do the table thing one more time here. So I've got an x of 3 that I want to approach, and if the limit exists, I have to approach it from the left. So I have to get really, really close from the left. and then I have to get really, really close from the right, like we've been doing with the table. And then we figure out our slopes in the second column there. So let me write those out. Let's figure out what f of a is, because we're going to use this in every one of our calculations. So that would be f of 3, which is equal to 3 squared, which is equal to 9. So f of a is going to be 9. All right, so I'm going to write this all out. Okay, so I wrote all that out to shorten the video a little. All right, and if I go ahead and I type those into the calculator, I should be approaching, coming from the left and coming from the right, the slope of the tangent line at 3. So I found that I got 5.9, 5.99, 5.999, and then of course undefined, and then from the other direction 6001, 601, and 6.1. So we appear to be approaching 6. So our conclusion that we're going to state is, therefore, the slope of the tangent line is equal to the derivative evaluated at 3. That's saying the same thing, and it should be 6. All right, so it's a lot of trouble to use the table, but we could always do that still, and that was our only tool that we had in our prior chapter. So what we say here is that the derivative of the function f evaluated at 3 is the instantaneous slope of the line, which is the same thing as saying that that's the slope of the tangent line. The instantaneous slope, the slope of the tangent line, and the derivative evaluated at 3 are all the same thing. Example 6 says, use definition 4. So this is definition 4. F prime of a, which is the derivative of the function f evaluated at a, is this limit expression here. So we're going to use that to find the derivative f prime of 1. So a is equal to 1 of f of x is equal to x cubed minus 5 at a is equal to 1, and then find the equation of the tangent line to f of x at a is equal to 1. So once we find the slope of the tangent line, we're going to use that to write the linear equation for the tangent line. All right, so first we're going to find out what is the slope of the tangent line at a is equal to 1, and we're going to use this limit definition. So let's write that over here. This is going to be the slope of our tangent line once we figure it out. So substituting in, we've got f prime of a is equal to 1 is the limit as h approaches 0 of the function, where we're going to substitute a plus h into the function. A is 1, so 1 plus h, then cube that. Everywhere where you have an x, you're going to substitute 1 plus h, which is a plus h. Then I've got the minus 5. So I substituted 1 plus h right here where the x is. Then I cube it. Then I've got minus 5. That's this part here. Now I have a minus right here. And then I evaluate my function at a by plugging in 1 into the function. So let's just write 1 cubed minus 5. We'll figure out what that number is. All over h. So that's the limit as h approaches 0 of 1 plus h, 1 plus h, 3 times 1 plus h minus 5 minus, and that number is 1 cubed minus 5, which would be 1 minus 5, which is minus 4, all divided by h. So we got to expand that. So that's 1 plus 1h plus 1h plus h squared times 1 plus h, and then it's negative 5 plus 4, which would be minus 1. All right, so I'm going to keep going until I've got this simplified. So that's 2h plus h squared times 1 plus h minus 1. All right, so now I got to distribute this again. So 1 distributed to 1 plus 2h plus h squared plus h distributed to that, which would be h plus 2h squared plus h cubed, and then I have minus 1. All right, so you guys can distribute, so I'm just going through this rather quickly. So I can see that 1 minus 1 is going to cancel out. So I've got 2h plus h squared plus another h plus 2h squared plus h cubed. So there are some like terms there. So that's 3h plus 3h squared plus h cubed divided by h. Right, now so you can cancel if you have an h in every term. So that one will cancel, and we'll have 2 left here. So we're left with 3 plus 3h plus h squared, and we're taking the limit as h approaches 0 of that polynomial. So we can evaluate it by just substituting 0 for h, so I'll get 3. So this is the slope of the tangent line, 3. Now let's go back to the beginning and see what it is we were asked to do once we've found that. Okay, then we're supposed to find the equation of the tangent line to f of x where a is equal to 1. All right, now I ran out of room, so let me create some room here. Okay, so that's where what we have now. We know the slope of the tangent line for this function at x is equal to 1 is 3. All right, so if I want to find the equation of the tangent line, I'm going to use the point slope formula. So I want a point. I've got the slope. So my point is 1. 1's my x value. So my y value is going to be 1 cubed minus 5. That's minus 4. All right, so the point slope formula says y minus y1 is equal to m times x minus x1. Or these values over here, we'll put the subscripts on. So the y here and the x here are just x and y, which will stay in the equation. All right, so now doing the substitution, I've got y minus y1, that's negative 4, m is 3, x minus 1. So that's y plus 4 is equal to 3x minus 3. So that's y is equal to 3x. Subtracting 4 from both sides, I'm going to get 7. All right, so you want to get it down to slope-intercept form, which is y is equal to mx plus b. All right, so that's the equation of the tangent line at the point 1, negative 4 of this curve. So just to make sure you understand what we found, this is a cubic translated down by 5, so I made a rough sketch. So we found the slope of the tangent line hitting that curve right there at this point here, which is 1, negative 4. So we can see that it's a positive slope. It's got a negative y-intercept, so that looks good. All right? Example 7 says use definition for, again, so we're going to find the slope of the tangent line as the derivative, and then once we find that, we're going to find the equation of the tangent line to the function at a point. All right, so let's go ahead and do our substitutions first. So we're going to find the slope of the tangent line is equal to the derivative evaluated at 1. So that's a limit as h approaches 0. This is called the limit definition of a derivative. So we're going to substitute 1 for a. 1 for a so far. So that's the limit as h approaches 0. So 1 plus h goes in wherever I have an x. So 1 plus h right here where I have an x. Plus 8, that's the first part, minus f of 1, so that's 1 where I have an x, plus 8, so that's going to be the square root of 9 over h. So that's the square root of 9 plus h minus the square root of 9, which would be 3 over h. Alright, so now, if I want to evaluate that limit, I'm going to have to multiply by the conjugate, like we know we have to do when you've got a difference involving a square root. Alright, so I'm going to multiply by the square root of 9 plus h plus 3, top and bottom, which is the same thing as multiplying by 1. Alright, so we'll see if this will get us into a form where we can evaluate the limit. So I've got the square root times the square root, so that's going to come off. Then I've got plus 3 times the square root of 9 plus h, and of course you would expect these to cancel in the middle. And then minus 9. And then you don't want to distribute because you want to see if you can get some canceling going on so you can evaluate it when h approaches 0. Alright, so this is going to cancel here. 9 minus 9. So we're left with h on top. So I can see that I will cancel that h and I'll have a 1 on top. So I can evaluate this limit now that h is not alone in the denominator causing a divide by 0 error. Alright, so since this is a rational function, I can substitute 0 in there. Well, it's a combination of a rational function and a square root function, a composition. But a composition of two continuous functions is continuous, so I can substitute 0 in for h. So that's going to be the square root of 9. So that's 1 over 3 plus 3, which is 1/6. Alright, so that's the slope of the tangent line that we found. Now what we were asked to do was to find the equation of the tangent line itself. So that means we're going to use the point slope formula again. So we have our slope, that's 1/6. We know that our x value is, wasn't it 1? Our x value is 1. So we need to find the y value, f of 1, which is 3. 1 plus 8 is 9. The square root of 9 is 3. So this is 3 right here. So we have a point, 1, 3. So this is x1, y1 in our point slope formula. So we've got y minus y1 equals to m times x minus x1. And that's y minus 3 is equal to 1/6 times x minus 1. Alright, so let's see if I ran out of room here. So that's y minus 3 is equal to 1/6 times x minus 1/6. So that's y is equal to 1/6 x, and then I've got minus 1/6 plus 3, and we need some 6 there, so that's 18/6. So that's y is equal to 1/6 x plus 18 minus 1 is 17. Alright, so that's our equation of the tangent line. And you want to get it in y is equal to mx plus b form by simplifying point slope formula. So example 8 says use definition 4 again to find f prime of 4. So the slope of the tangent line as the derivative evaluated at x is equal to 4. Alright, so we're going to use the limit definition of a derivative. Alright, so let's do our substitutions. We've got f prime of 4 is equal to the limit as h approaches 0 of f of 4 plus h minus f of 4 divided by h, which is the limit as h approaches 0. In the function, I'm going to substitute 4 plus h for x. And then I'm going to substitute 4 in the function. And then h in the denominator. So that's the same thing as 1 over the square root of 4 plus h minus 1/2 divided by h. Alright, so we're going to have to simplify that now because I can't evaluate the limit with the h going to 0 in the denominator. So we're going to find a common denominator, and the way that we're going to do that is we're going to multiply this fraction by 2 over 2 and this fraction by 4 plus h over square root of 4 plus h. Alright, so that's going to give us the limit as h approaches 0 of 2 minus the square root of 4 plus h divided by 2 times the square root of 4 plus h all over h. So I'm going to go ahead, I'm going to move that h out front so it's not in the way. So let's put it over here. Which is still dividing, which is fine. Alright, so I need to multiply by 2 plus square root of 4 plus h because I've got a difference involving a square root, which I'm going to use to simplify my limit so I can evaluate it. Alright, so I've got all that. Alright, so that's, we got to do some simplifying here. So I've got 2 times 2, that's 4, plus 2 square root of 4 plus h minus 2 square root of 4 plus h. And then I've got minus 4 plus h, radical off. And then in the bottom I've got 2 square root of 4 plus h. And remember, I'm not going to simplify the bottom so I can see if anything cancels. Okay, so I do know that these are going to cancel here. So I've got 4 and I've got minus 4, and this allows the h to cancel, but I've got a minus 1 left on the top. Right, so what I'm left with now is the limit as h approaches 0 of minus 1 divided by 2 times the square root of 4 plus h times 2 plus the square root of 2 plus the square root of 4 plus h. And that I can evaluate at 0. So I can just substitute 0 in for h. Alright, so that's negative 1 over 2 times 2 is 4, and 2 plus 2 is 4. So it looks like I have 16 in the denominator. Alright, so this is the slope of the tangent line right here. So now we want to find the equation of the tangent line. Now we have the slope. This would be your x value here. So we need our point. Alright, so we've got the slope, the point. So our function, remember, was 1 over the square root of x. So if x is 4, that's 1 over the square root of 4, which is 2. 1/2. All right, so there's our point. So we've got y minus y1 is equal to m times x minus x1. So we're going to put this in y is equal to mx plus b form. So that's going to reduce 1/4. Alright, so let's see if I have any more room. So let's go over here. So I've got y is equal to negative 1/16 x. I'm going to add 1/2 to 1/4. So that's 3/4. Alright, so this is the equation of the tangent line at the point 4 1/2. So we did it. Alright, so let's do an application problem here. A ball is dropped from a height of 64 feet. Its height above the ground at time t is given by the function h of t. So function h of t minus 16t squared plus 64 over the t interval 0 to 2. Use the limit definition of a derivative to find the instantaneous velocity 1 second after it is dropped. Alright, so the instantaneous velocity is the same thing as the slope of the tangent line. Alright, so remember our vocabulary from our prior chapter. Alright, so we need the limit definition of a derivative, so let's write that down. Okay, so there's two h's in this equation here. We have an h in our limit definition. H approaches 0 of f of a plus h minus f of a divided by h. So let's just call this one y so we don't get confused. Or we can just call it f. Function f of t. We don't have to call it h. We don't want the variables to confuse you. Okay, so that's f of t is the height of the ball as it's falling. Alright, so now we're going to do our substitution. So we've got the limit as h approaches 0, substituting a plus h into the function. A is, what's a? A is 1. Let's go ahead and substitute that. A is 1. So everywhere I have a t in my function, I'm going to put in 1 plus h plus 64 minus the function evaluated at 1. So that would be minus 16 times 1 squared plus 64. Alright, so that's the limit as h approaches 0 of, let's see, we need a square here, of minus 16 times 1 plus h squared, 1 plus h plus 64. Alright, so that would be plus 16 minus 64. So we can just go ahead and cancel those. Alright, so that's equal to the limit as h approaches 0 of negative 16 times 1 plus h plus h plus h squared plus 16, which is, if I distribute that, this is 2h. So that's minus 32h minus 16h squared plus 16. Alright, looks like the 16s are going to cancel. So that means I've got the limit. Let's see what happened to our h in the bottom. The limit as h approaches 0 of minus 32h minus 16h squared over h. Alright, so I can cancel h here and here and here, which leaves me with negative 32 minus 16h, and that's it. All right, so now if I evaluate that when h is equal to 0, I'll just get the slope of the tangent line, which is the limit evaluated as h approaches 0. So the only thing left is negative 32. So, like we said with our vocabulary, the instantaneous velocity is the same thing as the slope of the tangent line. All right. So in units, if we're working in feet, then velocity is going to be minus 32 feet per second. All right, and that was evaluated at a time t is equal to 1 second. So I can actually put a 1 in here. This is the velocity evaluated at 1. All right, so that means the same thing as the slope of the tangent line. So one more application problem here. This is our last problem. It says the local hardware store is charging $3.50 for ice scrapers. The daily profit earned by charging S dollars per ice scraper is given by this function here. So this is a profit function. P of S, where S is how much it costs per scraper, is this function here, a quadratic. So we're asked to find P prime, which is the derivative of the profit function evaluated when S is equal to 3.50, which is the cost of one of these scrapers. And determine whether the hardware store should raise or lower the price on their ice scrapers in order to increase its profit. All right, so what we're going to do is we're going to find the slope of the profit function, and if the slope is decreasing as the price increases, we're going to say you need to not increase the price of the scraper or you're going to lose money. All right, your profit's going to go down. So if we get a negative slope, that means at $3.50 that the profit is decreasing when you increase the cost of your scraper just a little bit. That's the interpretation. All right, so let's find P prime of S. So this is our limit definition of the derivative. So our A value is 3.5. We can drop that 0. All right, so this is the limit as h approaches 0. So we can say over here this is going to be P prime, the slope of the tangent line when the scrapers cost $3.50 each. So I'm going to plug in A plus h into my function. All right, so let's go ahead and shorten this as much as we can. A is 3.5. All right, so that's here. Now I need it here as well. And then I've got minus 12. All right, so now we need P of 3.5. Let's just figure that out. Let me write it down here so I don't have so many numbers here. P of 3.5, and that's going to go right here. I'm going to get a number for that. So that's negative 21 times 3.5 squared plus 125 times 3.5 minus 12. All right, so I got a number for that. I got 168.25. All right, so I don't have to have all of that there. Okay, so now I got to simplify this a little bit, and I need my h on the bottom. I'll put it out here. All right, so that's the limit as h approaches 0 of 1 over h times negative 21 times 3.5 squared, that's 12.25, plus 3.5h plus 3.5h, that's 7h, and then h times h is h squared. So 125 times 3.5 is 437.5, 125h. Then I've got minus 12 minus 168.25. Alright, so I've got all that. Now let's just keep simplifying. Let me scoot it over a little bit. So I've got minus 21 times 12.5. That's that number. Minus 21 times 7. Minus 21 times h squared. Then I've got this number, 437.5. I've got this number, minus 12. So I can combine all those numbers. And then I've got that 125h. Alright, so I plugged all those numbers that I underlined in, and I got 257.25. Alright, so now let's see what cancels. So this is going to cancel. And then I've got negative 147 plus 125h. So that's negative 22h minus 21h squared. And then I've got my h on the bottom there, which now I can cancel it. Alright, so I can take the limit of this now of negative 22 minus 21h. So I'm just going to substitute 0 in for h, and I'll get negative 22. So this is the slope of the tangent line at x is equal to $3.50, which is the price of the scraper. Okay, so we found out that we have a negative slope, which means you're trending downward. That means if you increase your price a little bit more, your profit is going to go down, right? Think about it this way: if I'm here and I go a little bit more here, then my price is going to sink. All right? So that means I do not want to increase the cost of my scrapers because my profit will go down. So we're going to say negative slope, do not increase the cost of the scraper. Or your profit will decrease. That's what your negative slope is telling you. All right. Okay, so that ends our lecture. So you should have enough information now to go ahead and start your homework section on the section called Defining the Derivative. Let me know if you run into any questions.